So, this is Paul Gregg, and this is documentation of my second roller coaster, the biggest one, the 3D-02 track and coaster. And there's two carts for it, but this is I'll document the second cart in another video. So this is my grandson on the first roller coaster I made. It's just out and back reversing roller coaster. A lot of fun, but real easy to build. The cart especially, just four wheels that all are fixed to the frame. This is, I guess, a page of why I'm doing this, I suppose. I don't know. It's kind of crazy. But it is kind of a little adventure, and I guess that's why I'm doing it. And the kids have a lot of fun with it, but keeps me busy, I guess, out of trouble. So we're going to talk a lot about roll, pitch, and yaw. And this is important. I don't want to stop and explain this every time, but basically, if you're riding in a roller coaster, these are aeronautical terms. Roll is if you tilt the wings back and forth, that's a roll. So in that axis, that's a roll. Pitch is when you point the nose up or down. And that's when your roller coaster is going up and down. That's pitch, pitch down, pitch up. And then yaw is where just the roller coaster is spinning in a horizontal plane. So when I talk about roll, pitch, and yaw, these are aeronautical terms, but it also works for the roller coaster. So get those in your head. This is starting out more than a year ago, looking at a three-dimensional roller coaster as opposed to the first two-dimensional roller coaster. It's going to be a lot more complicated. The plastic pipes with bank turns, that'll be more difficult to build, but relatively easy compared to the cart. A three-dimensional cart is much more difficult than a 2D cart because it has to not only accommodate the peaks and valleys of a two-dimensional track, but also the left and right curves and bank track of a complex path. So when there's a 3D shape to the track, only if all the wheels were fixed, then only three of them would be in contact at any one time. You'd have to have a lot of a lot of sloppiness in it. And that would be an unacceptably rough ride, threat to safety. So that's just what I'm proposing. Looking around, it's hard to tell on professional roller coasters what the undersides look like. I looked online at all the pictures I could and kind of started there and ended up kind of coming up with this. And I think it probably replicates what most professional roller coasters do. You just can't see it. The front wheels will have roll and yaw and pitch freedom of motion. The pitch freedom comes from just at the wheel level, but the front bogie, the bar that connects the two front wheels, will have rolling freedom and yaw freedom. So it can conform to whatever direction the track's taking it. The two back wheels and a point in the middle of the front pivot crossbar define the plane of the cart. And I'll show you some of the mechanisms. I won't go through this too much in detail. I'll talk about dynamic stability in a little bit. I did want to use just 4 main wheels instead of 8. The less wheels, the less drag, weight, cost. Probably go back on that now, but at the time I really wanted to try to make a 4-wheel cart, 4 main wheels. But I was also at the time thinking for heavier riders and probably a better design, I was thinking of a 2-wheel truck design at the same time. So we always start out when we do an engineering project with what our design requirements and objectives are. Design requirement is something you have to do. An objective is something that would be good to do. So I really want to provide a fun ride for kids with 2 to 3 G's acceleration, high initial drop, and nice bank turns. My grandkids, 5 to 9 years old, between 40 and 90 pounds. I want this to be pretty big, 180 feet around a circuit, not just an oval, but something kind of complex. And then with low velocity at the very end, so I can just kind of grab it and stop it and push it back up the lift hill. And then for safety, I put in the upstop wheels on the bottom of the track so it can't ever come off. Factor safety, I've explained that in other videos, but basically make it really safe. And then there's a list of safety rules that I've gone over in other videos. You can stop and read them here. And then I have a certification process, just like we do in aerospace things. I did heavy cart static tests where I rolled, really it was 830 pounds down a 10-foot test track, and that's documented in another video. And then I also, every track I make, I do heavy cart dynamic tests where I put 1.5 times the maximum that I ever expect to have a rider weigh, and run it around a few times and check for any cracking or permanent deflection in any parts. So this is just what happened. This is the way I did it. If this is not in the best order, or I don't present this in the best way, forgive me. I came up with this. I knew I wanted to do yaw and roll freedom in the front end, so I developed this new system for doing this. Used a big bolt here for this horizontal one, 7/16 grade 8, because I knew it was going to take a lot of stress. And all the other bolts pretty much are grade 5, 5/16 diameter. The side wheels are located a little bit aft of the main wheels, so they can keep things tracking well. If I can keep this whole thing light, then it'll move a lot better. Up to this point, I was really longboard and skateboard wheels. I was really looking at those only, and but thinking about this, longboard and skateboard wheels have some stickiness to them, so that the skateboarder can, when he goes around a turn, he has some traction. But that's really, you don't need that. You don't want that in a roller coaster. So the harder wheels that I can get, probably the less friction there's going to be on this, because there is a little bit of side slip, and the harder surfaces have less friction between them. So I've started making my side wheels. I couldn't find a wheel that I wanted, a nice wide, small diameter wheel, and I just these are 3/4 PVC couplers that are with two bearings in the ends of them, and they seem to spin up really quick and seem to be working. Like I said, I was trying to make just get by with 4 wheels. I probably wouldn't do that now, but this really did turn out well. This is the first card I made for the 3D track. I tried it out on my 2D track, and it just scooted along there like crazy. So it was very promising. One disadvantage to this is that my side wheels don't track orthogonal or 90 degrees to the side of the rail, and when they do touch, there's some slide slipping there, and that's a source of friction. This is just kind of clamping the front and the back end together where I started. And, so you can see that this does have roll, degree of freedom, and yaw, and spin back and forth. And it's light, so it spins back and forth pretty quickly. I tried that out on my track. It just scooted really well. It's about 10 pounds here, so it's a very light cart at this point. That's the welded cart. You're always kind of going between how high the cart's getting. You want it at a certain height so it won't hit the ties between the wheels. But you're trying to get the center of gravity low as you can, so it's always a design challenge to kind of say, well, what's the best load path here? But I still don't want to get this too high. One thing I'll point out here is I'm not a good welder. I'm a terrible welder, especially at this point in time. I was a terrible welder, but I do know how to design for welds from my experience in aerospace. And there's a guy named Omer Blodgett, world welding expert. He has some books out that tell you how to design for welding, and recommend taking a look at that website. Downloading his things is really interesting. For instance, you can see these welds. Instead of just butt welding the frame together in the corners, which would result in fairly small joint area, I run these lower frames 1/8 of an inch past this cross frame, and then put a fillet weld in there. And then I did the same thing here. I stick this out 1/8 of an inch, do a fillet weld on the bottom. So I've got inch and a half, 3 inches, 4, 5 inches of weld holding that joint together, instead of just an inch and a half or something if I'd butt welded it. I did have to give up some vertical space there maybe, but you can see here I stick them out in front of the cross member there so that I can get fillet welds under them. So fillet welds are much better than butt welds, and try to maximize the length of weld that's holding pieces together. And I think it comes out much better design. The stresses are lower in the welds. It's going to last longer. Short side subject, static and dynamic stability. When I talk about stability, it means that everything wants to kind of go to a stable equilibrium place, like if a ball was in a trough. Unstable means that it's on a hill and it's ready to go off to either side really easy. Generally, you want to work toward a stable design, but getting near instability is helpful if you want highly responsive design. In other words, it turns quickly. So I put the wheels in back of this front bar, in back of the pivot here, so that makes a little bit of dynamic stability, but it's still pretty close so that the thing can spin really quickly. This is off subject, but I did start making a 2-wheel truck assembly for an 8-wheel cart, and I'll cover that in another video. But you can see my axles are high on these cross members here, this truck frame, and my axle that goes in is low, so that's naturally stable, dynamically stable. So in design, you'd always try to think about dynamic static stability. A little bit of a side subject, but this is also covered elsewhere. Basically, it says the white PVC pipe that's used for plumbing is not ultraviolet resistant and brittle in exposure to sunlight. I've been trying the ABS black plastic sewer pipe, which, because it sticks out of roofs, they put carbon black in it to make it sunlight resistant. But it's not very stiff or strong. But if you don't want to have to preform the pipes, and that's when I was at the stage of making my first roller coaster, I just used ABS pipe, and it seems to have worked out pretty well. Nowadays, I use PVC conduit, which has chemicals in it that make it supposedly sunlight resistant. I'm doing some studies on how sunlight resistant it really is. And I did coat the whole thing with Aerospace 303, which is supposed to be a PVC protectant for polymers. I didn't know how stiff, I bought a couple of pipes at the hardware store, PVC and ABS, same diameter, and I wanted to kind of characterize the relative stiffness. And when you don't really, I couldn't find anything online, so I did a test. I just put what you'd call a fish scale on there and pushed down on it, keep track of the deflection and the load, and found out load divided by deflection for ABS is this number, PVC is this number. So the PVC is about twice as stiff as the ABS. Online, the PVC and ABS properties, the PVC is about 35 megapascals. That's a metric unit of stress or strength, compared to about half of that 18.5 megapascals for the ABS. So it's probably a good idea to stick with the PVC conduit unless you're in an area that, unless you don't know how to do the forming, or it's an area that doesn't matter. This is basically, I separated the hot forming that I learned about here, the hot sand forming of pipes, to another video that you can look at. But this is how I determined the radii that I wanted for a bank angle of a certain angle. I've covered that elsewhere too. So here, now that I started to, now that I knew how to bend these pipes into smaller radius, really constant radius and smaller radius, then I'm probably going to have to go back and change this cart. The front end looks really good, can bend, can turn 20 degrees in yaw and looks all good, but the back end, you can see this would be a lot of side slip drag if you just left this like it was. I started off trying to think that maybe I could have fixed wheels on the back, and it's obviously looking like that's going to cause some drag, so I'm going to have to redo that. So I deliberately switch between track and cart development every couple of days. This process of enhancement is really useful in engineering, where you can kind of make improvements on one side, then go over to the other side. So now that I have these really tight turns, I need a better cart with some things. So here's really the really fun part of putting a track together, is when you start sticking things off into space and temporarily putting a ladder under it or something, and come and put a little truss frame under it, and start seeing how this track's really going to work. So at the same time, I was developing the analysis method for the track, and I got a little ahead of myself here and didn't do the full analysis and didn't get the optimum angles in and some of that. So I rebuilt some of this track later on. But things are looking really fun, looking really good. So this is before modification to the aft wheels. You can see they're fixed. It doesn't look very good. And so what I tried something a little different here. There's two types of steering for a roller coaster cart, what is called a bogie steering method and an Ackerman steering. You can look that up. There's a nice article on Wikipedia down here. And this is afterwards. I stayed with the bogie steering in the front end, but I made casters and let these wheels on the back pivot, so now they'll conform and track better. Around corners and in straights, there's a little bit of a difference here. I think I did the math here in a CAD system. The apparent width of the track gets a little smaller in a curve, but that's within the tolerances of what these Ackerman style wheels could take in the back. And so it was okay. Went out every couple of days and ran it around the track and saw what was going on, and things were looking pretty good at that point. So that's just, I could do the math on this, but sometimes it's just easier to put it in a computer-aided design program and just measure things after. This is what I was after, this little distance between the center of the wheel and the center of the track. This is an interesting thing I sort of fell into with these Ackerman style cast wheels in casters. The cart really didn't want to go backwards because these would kind of splay out and lock onto the track. So that was a good thing about the Ackerman wheels, is they wouldn't let the cart go backwards. I did have some trouble keeping these things stable. When I do design work, what you really want to be thinking about is what the load path is. And so there was a lot of going out and putting this on the track and pushing out on it, like simulating the centripetal force that would be on it in the overturning moment, overturning roll moment and stuff, and pushing on it and see how these things were working. And you can kind of visualize what the loads are. This is a load. The cart's trying to go that way, and the track is stopping it with these two wheels, how the loads are going through here. So I had to fiddle with just where these pieces were every once in a while. This is the aft wheel assembly. This is the forward wheel assembly. I did have to end up putting more side wheels on it, so it'd be a little more, be better. That became obvious as I started experimenting with this on the track. So here's the first dip and the first hump. It was really pretty radical. This is a pretty tight radius and was causing high. It was about this time I was starting to do the analysis too and trying to have that catch up to the track, and it was predicting some really high G's down in here, over 3. And but I thought, well, let's give it a try and see what happens. It was like a 63-degree drop into this 8.5-foot drop down here, and it was really moving fast. This, to take a little, I'll cover this here. You do this quite a bit as an engineer. This is what we call stress work. This is a very simple example. We do these just on pieces of paper to see if things are in the ballpark. This is an interesting one because I thought it wasn't adequate and had to modify it. So basically, I have a beam that represents the cross beam here. Did a free body diagram of it, and there's a load here, and half that load's on either side. So there's a kind of a cantilever here with this P/2 up there, and then there's bending stresses in here in this tubular section here. You have to know the material properties, what the stiffness of that steel is, and you also have to know the area moment of inertia of that rectangle, of that square tube shape, and that comes from the thickness and the dimensions of it. I have a separate spreadsheet that calculated that for me. I won't go into too much detail, but basically I see what the stresses are here, and then from the published stress of the steel, my initial bending stress, the moment times the distance to the outer fiber from the centroid divided by the area moment of inertia, is 49 KSI, and in English units. But the allowable stress of the steel is about 36 KSI. So whoops, that's not going to work. The margin of safety, which is different than the factor of safety, the margin of safety has to be above 0, or else it tells you it's not going to work. So in a typical engineering project, you do lots and lots of these. You calculate lots of details by methods similar to this and make sure all the margins are positive. This one was negative. It tells you you either got to lower the load somehow or you got to modify this. So I chose to modify it. This is before the modification. The modification's pretty simple. Put some spacers in there and weld a bar across the top. So now the moment of inertia is really high. Moment of inertia went up to this value here. So now the stresses by that same bending stress calculation are only 9,000, under 10 KSI. And the strength is 36 KSI. So now I have a very high margin, very strong. It's not going to break, and it's a lot stiffer. So this is another stress analysis on the shear of this bolt. The reason it's worth looking at is there's shear and bending on here, but had a very high margin here. This is a big bolt. The reason you want to kind of look at some of these is if this sheared off, you'd all of a sudden not have front wheels. If you were going really fast, you'd have a big crash. Some failures are just like, okay, like this one. What would happen is if I left it like this, the worst case that happened is this would bend a little bit and I would notice it and then I would replace it. If this bolt sheared off, then the front of the cart wouldn't have wheels and that would be a big disaster. So some failures are more critical than others. So then I started putting the track together. This is the old track. This is the first out and back negative G track, and this is the new one. It goes up to this 9-foot hill, goes down, gets a lot of speed, goes around a bunch of bank turns, goes through the trees, comes out in the yard again, goes under the negative G coaster, comes in here. Now, yeah, I didn't have a lot of room. I kind of cut this out and made it so that they're going real slow here. People were concerned that people's heads were going to get chopped off, but there's quite a bit, enough clearance there. And these are some pictures of intermediate stages of building the track. I start out with just the frames and then put longitudinal pieces in to stiffen it up, and then a brace up to every tie, and then some big diagonals in the end on these frames, which you'll see later, to really stiffen the whole thing up. If you've been following my channel, you know that I don't really like putting holes in cement and posts in my yard, and so that's why I build these frames. They're actually cheaper than 4x4 posts because they're made of 2x4s. I always put treated wood on the bottom brace, but 2x4 is pretty cheap, and so I think it comes out to about 20-30% cheaper than 4x4 posts, and it's a lot stiffer side to side, a lot better supported. So I did about this time get into the spreadsheets. There's a whole nother video that just covers the spreadsheet analysis, basically for different locations, like the top of the hill, the bottom of the first dip, up here, up at the top of this curve, down at this curve. You go around there 10 or 12 different spots, and you could have a lot more than that if you wanted to. Here's the top of the lift hill. It keeps track of the energy and how fast it would be going. Obviously, the top of the lift hill, it doesn't have any speed. And so there's, just 1g, gravity. At the bottom of the first dip, you're going 6.2 meters per second, and that added to gravity is over 3 Gs. Peak number 2, you're starting to turn. There's a bit of a turn radius there, so now you're getting some side centripetal forces, and what this reports is what the optimum bank angle would be. You can see down here a pretty fast portion here. There's a certain radius turn combined with an up-down radius, and so I get a 53-degree optimum bank down there, and that's why I banked it pretty high down there. I don't think I banked it 53 degrees, but you don't have to bank it perfectly, but you need to. It's a smoother ride if you kind of get it in the ballpark. But this is covered in another video, so I won't go into any more detail here. Setting up that track in my yard, I kind of moved. I got the first 50 feet done, and then I kept moving it back and forth to try to miss bushes and stuff. And so I had put a lot of stress on the number 10 3.5-inch long galvanized screws that were holding the whole thing together. And then I found that some of these screws were breaking off. And come to find out, this is not an uncommon thing for deck screws. If you hit a hard piece of wood, an impact driver, which is an impact drill, not a hammer drill, an impact drill can shear off a fastener. So it was more to do with hitting a hard piece of wood and using an impact drill. I also thought about, right now I've got 2 of these fasteners going in at an angle so that the main wheels and the side wheels don't hit the hole or the fastener head. It's countersunk out here too. So it sticks out a little bit, but it doesn't get hit by so the ride's just a lot smoother. And I thought about some modifications. If I needed to make it bigger, I could always just put more ties in there, space the ties closer. Or I could maybe come up from the bottom with a 3rd screw in between the top 2. And then I'm thinking, well, maybe screw from this angle going up is better anyway. So I don't know the answer to that, but there's lots of things I could do. This talks about pre-stresses. I won't go through the whole discussion, but basically, if you didn't pre-bend the tracks, you'd be cranking this pipes around and kind of screwing it down as you bent it, and maybe with 2 people, and that would leave a lot of what engineers call pre-stresses on the fasteners, and that means they've already got stress on them before the cart comes along, and so that would add to the stress. And in sunlight, maybe this PVC, if it's bent around a bunch of frames, maybe what we call creeps into position. In other words, the stress is reduced in time at temperature. I don't know about that, but it's always a good idea to, and much easier to build the track to hot form these pipes ahead of time with hot sand, which seemed to work really well. And that's covered in another video. About the same time, I thought, well, what happened if I slipped and fell and a kid went down this track backwards into part of a tight curve that wasn't banked, and would that be dangerous? So I came up with a very simple anti-rollback mechanism. It's just two 2x4s and a long bolt. It's just run by gravity. So when you push it this way, these things bend. These things just flop out of the way, and then they flip up and catch the back of the frame of the cart in case it wants to go backwards. So that's an extra safety thing. How much did this whole thing cost? So you're looking at not this out and back track, but this whole 180-foot PVC roller coaster track here. You total this up, won't go through all the details, but basically $35 for a 10-foot section of the PVC track with the wood. So 180 feet cost me $634. And I buy the stuff at Home Depot or Lowe's. The cart, assuming I did all my own work in the welding, which is most of the effort, and how many wheels you have and what quality the wheels are and the bearings could cost you more than this. But basically, I got the cart for under $150. The whole thing, I'm thinking, is under $1,000 and about 150 man hours. But I improved that a lot in the third one. I was able to make the third roller coaster in 2.5 weeks. It's a smaller coaster, but still. So there's a good learning curve there. When the track was done, this gets a little messy because we tried a few things and modified a few things. Everything I didn't like, I kind of rebuilt, and so we put 110 pounds of wood pellet bags in there and sent it around a few times, saw what was going on, then let some kids try it out. I put my smartphone in there with accelerometers and checked what the real accelerations were. This at first, like I said before, the first dip had like a 6-foot radius in it. It was really tight, and it was getting 3.5 Gs through there. And I thought, well, that's a little too much. So I don't really need that 63 drop angle. And I also at the same time did my 830-pound heavy static tests on the track, and that's covered in another video. So I learned a lot from that. I was trying to apply it here. So this is basically looking at the heavy cart tests. So then I thought this radius down here was just too much. It was just too, the accelerations, the centripetal accelerations are a function of the velocity squared divided by the radius. So the smaller the radius is, the more the acceleration is. And I thought that was just too much. So I rebuilt the whole thing, and it's much smoother here. It actually drops lower to a faster speed, but then it kind of comes up and looks better there. And that dropped the G's down to around 3 G's where I wanted them. And instead of 63 degrees here, I went to 55 degrees. But that allowed me to gain a little bit of headroom here. It's about 40 inches, which is plenty. It may look, I'm sure when you're riding the cart, it looks like it's less than that, but it's adequate. It's plenty. I didn't want to. The trouble was I kept raising this to add headroom here, but then the cart really slows down here and goes slow right there, which I'd rather went faster, but I couldn't drop it very much because then I'd have less headroom here. So that was a bit of a trade-off there I was working with. I did put in 2 more of these anti-rollback mechanisms, and these didn't totally work with gravity very well, so I put some bungee cords on them. But I modified this track a second time. Well, I was doing it a third time. When I was modifying it a second time, I tried to just crank it down and screw it down and then apply a blowtorch to the sides and heat it up so it would kind of relieve the stresses and bend. But anytime you put a torch on something, you're going to heat one portion more than the other, and all the bending happens at that spot. So I redid this whole front section of track, and it turned out a lot smoother. Efficiency, well, I measured the height between where it starts at the top and where it ends up. When it rolls, it has a little bit of speed and comes back up. So the total pretty much is 8 feet of vertical drop in 100 feet well, no. I'm saying my measure of efficiency, if it was 8% average drag, then it would be a track that would drop 8 feet in every 100 feet. I assumed, I think, so 4 to 5% drag on it as an average over the whole thing. I talk about that in another video too, so I don't have to do it too much. But I measured a total vertical drop of 86 inches from the top of the hill with no velocity to the final stop position. And that divided by the 170 feet is 0.0421, so 4.21%. The efficiency is around 96%, so that's pretty good. It's a pretty smooth track. Things track pretty well. I won't go through the rest of this. I've covered most of it in other videos, but basically I did, the only other thing I'd say is these frames, these 2x4 frames, I put a counterbore 3.5-inch number 10 screw in the bottom, 2 of those down there, 2 here, maybe 1 up through the bottom and 1 through the side. There's a counterbore number 10 screw holding these 2 together, and then there's 3 on top through the tie, 1 into the inside board and 2 into the other one. So that's a pretty simple frame, and it's worked out really well. That's how I build my frames. And I think that's where I'll stop. So thanks for watching.